Here are the top 10 things you must know about functions. Must know number 1. What is a function? A function is a relationship between two variables where each input corresponds to exactly one output. And to help you understand this definition, let me give you an example of a relationship that is a function, such as y equals 2x squared minus 5, and a relationship that is not a function, such as x equals y squared. Both of these equations show the relationship between the variables x and y. But relationships can be shown not just in equations. We could also make a table or draw a graph that shows the relationship. And from those tables and graphs, we'll be able to more clearly tell why this one is a function, but this one is not. So let me make a table of values for both of these. For y equals 2x squared minus 5, I'll pick x values between -2 and 2, and then I could take all of these x values and use those as inputs into my equation for x, and then do the calculation 2x squared minus 5 to get the output value of y. And because it's able to output these single values for y for each of these input values x, we know that this relationship y equals 2x squared minus 5 is a function. And I'll plot all of these points to get a rough sketch of its graph as well. And now for the relationship x equals y squared, let me make a table of values. And then because x is isolated, it would actually be easier to choose values for y and then calculate x. So I'll choose y values between -2 and 2, and then the equation tells me the x values are equal to the y values squared. So I'll just square all of these y values to get the x values. And then if we use this table of values to look at the relationship between x and y, I notice that when x is 4, y could be either -2 or +2. So there are two different y values for the same x value. So when x is 4, it's able to output two different values, both -2 and 2. That's why this is not a function. And let me show you what the graph of this looks like by plotting all of those points. And now that we have the graphs of both of these relationships, I'm going to show you a really easy way to tell from the graph if a relationship is a function or not. It's something called the vertical line test. If any vertical line touches a graph more than once, the graph is not a function. So if I look at this graph of the relationship x equals y squared, it should be obvious that this is not a function because it would fail the vertical line test. For example, if I drew a vertical line through x equals 4, you could see it touches the graph of this relationship in two different spots. If any vertical line you can draw touches the relationship in more than one spot, it's not a function. It fails the vertical line test, right? This demonstrates that when x is 4, y can be both 2 and -2. There are two different output values, y, for the same input value, x. But if we look at the graph of the relationship y equals 2x squared minus 5, which is a function, there is no vertical line I could draw anywhere that would touch this relationship in more than one spot. Any vertical line I draw would just touch the relationship in one spot. For example, a vertical line drawn at x equals 1 would just touch the relationship right down here at a y value of -3. And before I move on to the last section, I actually want to take a second and show you a notation we use when we have a function. So for this function, y equals 2x squared minus 5, we actually don't write y. We want to actually give this function a name. And by convention, it's most typical to use the letter f to name the function. So function notation looks like this. Now, this does not mean f multiplied by x. It means f of or f at x. This f is just the name of the function, and this x is just the independent variable, which we call the input of the function. And this 2x squared minus 5, right, the operations we do to the input value, are what we call the output of the function. So this f of x notation is just function notation that means the y value of the function. Right, this f of x is equal to 2x squared minus 5, which is the output. And this f of x notation just names the function. Usually we use f, but it could be any letter. And then beside it is a place where the input goes when you're evaluating a function at a certain value of x. So for example, for this function, I know when x is -2, y is 3. We could show that using function notation by saying f at -2 is equal to 2 times the input value, which we've written here. We're inputting -2 for the x, so I'm going to replace the x in the equation with my input value of -2 squared minus 5. And then evaluating the output by doing 2 times negative 2 squared minus 5, I get an output, or y value, of 3. So this function notation, f of negative 2 equals 3, just means when x is negative 2, y is 3. This is saying the y value of the function, when the input, x value is negative 2, is equal to 3. Must know number 2, domain and range. Domain is the set of all possible input values that output a real value. So it's the set of all possible x values that you can sub into the function. Whereas the range is the set of all possible output values that a function can produce. So it's the set of all possible y values. And to demonstrate this, let's look at a function, f of x equals x squared plus 1. Let's start by making a graphical representation of this relationship between x and y, and then I'll show you how we can use both the equation and the graph to determine the domain and range. So to make the graph, it might be useful to start by making a table of values for this relationship. I'll choose x values between negative 2 and 2, and then use each of these x values as the inputs for x into my function. And then I'll be able to calculate the output value by doing x squared plus 1. So if I use negative 2 for my input value, f at negative 2 would equal negative 2 squared plus 1. So f of negative 2 would equal 5, which means when the input x is negative 2, the output value y is 5. And then inputting the remaining x values, I get these output values for y. And I'll plot all of those on my graph. And now I want to be able to analyze this graph and this equation to state both the domain and the range of my function. When determining the domain, I need to find the set of all possible input values that will output a real value. So I just want to figure out what values for x am I able to input for this x in this equation to be able to output a value for y. Well, you can input any real number for this x, and the output will be a real value, right? Any real number can be squared. So there would be no restrictions on what we could sub in for x. Or graphically, since we're interested in the possible x values that this function could have, we're just looking at graphically, how wide does this parabola get? Or horizontally, where does this function exist? And this parabola, it does continue forever. It's going to get infinitely wide. Right? When x is 9, let's say, we would be able to calculate a value for y. It would be really high. It would be at a y value of 82, but it does exist. And same in the negative direction. No matter how far you go in the negative direction, if you look up high enough, you would be able to see the graph of the parabola there. So we can say that the domain is just the set of all real numbers. And we write it like this. We say x is an element of the real number set. The real number set includes all rational and irrational numbers. Anything can be subbed in for this x, and you would be able to get a value for y. Or instead of writing domain in this set notation, you could write it as an interval of x values. You could say the domain is the interval of x values from negative infinity to positive infinity, which just means any x value between negative infinity and infinity is a valid input value for the x in our equation. And now for range, we would be looking for what are the possible output values we can get for our function. So what can x squared plus 1 equal? Well, because x squared is always going to be at least 0, when we add 1 to it, we're going to get a value that's at least 1. So the smallest y value we can actually get is 1. And we can see that on the graph, right? When thinking about the range, we would be thinking vertically, where does this function exist? Well, notice it's never below that point right there, which has a y value of 1. So vertically, it's always at 1, right? That point has a y value of 1, or above. It does go infinitely high. So to write the range inside of curly brackets, we say y could be any real number, so it's within the set of real numbers, given, we use a vertical line, y is greater than or equal to 1. Or writing this in interval notation, we could say the interval of y values would be from 1, right? The lowest y value is 1, and we want to include 1, so actually write a square bracket to include 1, comma, the highest y value could have, well, it goes infinitely high, so it would go from 1 to infinity, and always a round bracket at infinity. number 3, common types of functions. You should be very familiar with the shapes of a few different common functions that you'll run into a lot. The first ones I'll show you are the shapes of the first 3 power functions. F of x equals x to the power of 1, which is just a linear relationship with a y-intercept of 0 and a slope of 1. F of x equals x squared, which is a quadratic, so it has a parabola shape. And next is f of x equals x cubed, which makes a bit of an S shape through the origin. So those are examples of power functions. And next, you should know the square root function, which is the function f of x equals the square root of x, where we calculate the output value y just by square rooting the input value x. Square root of 0 is 0, square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So those are a few points that I could graph. And for this function, it only exists at 0 or to the right. So the domain of this function, x has to be greater than or equal to 0. And that's because if I were to input a value of x less than 0, so if I put in a negative value for x, the square root of a negative number is not a real number. So it would not output a real value. Next, let me show you the graph of the rational function, the function f of x equals 1 over x. Now this function actually has 2 asymptotes. It has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. And we'll spend time later in this video talking more about asymptotes. But just for now, know that these are lines that the function is going to approach more and more closely, but never touch. And the graph of this 1 over x is actually broken into 2 branches, so its shape is called a hyperbola, and it looks like this. And now let's continue on. I want to show you 3 more graphs. You should know the shapes of common trig functions, exponential, and logarithmic functions. Starting with trig functions, we could look at the graph of f of x equals sine x, which is a sinusoidal wave that starts at 0 and then oscillates up and down between 1 and negative 1. And this is a periodic function, so the pattern of y values just repeats over and over and over again, creating this wave shape. And the graph of cos x looks similar. It's still this periodic wave that oscillates between negative 1 and 1. Notice it's just like a sine function that has been shifted to the left. And now let's look at both exponential and logarithmic functions, which are inverses of each other. So there's going to be relationships between them. An example exponential function could be f of x equals 2 to the power of x. For this function, any real number could be subbed in for x, so there's no restrictions on the domain, but the output value is always going to be bigger than 0. So there would be a horizontal asymptote at y equals 0. And this function 2 to the x, it grows very rapidly. It goes from 1 to 2 to 4, then to 8, and it just keeps on doubling as we move to the right. And as we move to the left, it would just keep getting cut in half, so we'll keep getting closer and closer to 0. So here's the graph of the exponential function 2 to the power of x, and you can see that it starts growing very rapidly as we move to the right. Whereas a logarithmic function, let's say f of x equals log base 2 of x, that's actually the inverse of the 2 to the x function, so it's the opposite. So it has a vertical asymptote at x equals 0, and it actually grows more and more slowly as we move to the right. So there's the graphs of 6 different types of functions where you should be very familiar with the shapes of their graphs. Must know number 4, transformations of functions. Let's say we have some parent function f of x. The graph of f of x could be transformed by stretching or compressing its graph, reflecting it, or shifting it. And we could do vertical transformations to the graph of f of x by applying operations to the whole output value of f of x. And if we wanted to do horizontal transformations, we would apply operations to the input value x. And we could give this new transformed function a name. I'll call it function g of x. So in this formula, it says that g of x is equal to a transformed version of f of x. These parameters, a, k, d, and c, transform the graph of f of x to give us our new transformed function, the function g of x. And we can get the graph of g of x from the graph of f of x by applying the following transformations. First off, the parameter c. That's what's being added to the output of the function. If c is greater than 0, the function shifts up. And if c is less than 0, the function shifts down. And next, the d value is the value that's being subtracted from the input of x. If the d value is positive, the function shifts right, and if d is negative, the function shifts left. Next, we'll look at the a value, which is what we multiply the output of the function by. If a is bigger than 1 or less than -1, it causes a vertical stretch by a factor of the absolute value of a. But if a is between -1 and 1, it causes a vertical compression by a factor of the absolute value of a. And if a is negative, that causes a vertical reflection. And let me make a bit of room. And lastly, we'll talk about the k value. The k value is being multiplied inside the input of the function. If k is bigger than 1 or less than -1, it's a horizontal compression by a factor of 1 over the absolute value of k. But if k is between -1 and 1, it's a horizontal stretch by 1 over the absolute value of k. And if k is less than 0, there's a horizontal reflection. So now that we have all of these rules, let me move them out of the way and we can try an example. This example says f of x equals x cubed, that's the parent function, and we want to graph the transformed function g of x, which is a transformed version of f of x. There are 3 transformations happening to it. We have an a value of 1/2, which would cause a vertical compression by a factor of 1/2, which means all of its y values are going to be cut in half. And then we have a d value of 2, right? The d value is what we're subtracting from x. Since we're subtracting a 2, the d value is 2, which means the function is going to shift right 2 units. So I would have to take all the points of f of x and shift them 2 to the right. So I would have to add 2 to all of the x coordinates. And then the c value is -1, which is going to shift the graph down 1 unit. So I would have to subtract 1 from the y coordinates of all of the points on the graph of f of x. And now let me do these transformations to the points of the parent function, x cubed. So I'll make a table of values for x cubed. Let me pick some x values for my parent function x cubed. I'll pick the x values between -2 and 2, and I can calculate the y values just by cubing them, right? F of x is equal to x cubed, so I just have to cube all of my x values. And let me plot that function on the graph that we have over here on the right. And now what we want to do is graph g of x, the transformed version of f of x. So I'm going to apply all of these transformations that we wrote down to these key points of our x cubed function. So I'll make a new table of values for g of x, where the transformations that are happening to x is I have to add 2 to shift it to the right, and to the y's, I have to cut them in half to vertically compress it by a factor of 1/2, and then I have to subtract 1 to shift it down 1. So I'll take all of the x values from my parent function and sub them into this little equation that I've made. So I basically just have to add 2 to all of these x values to get my new x values. And now I have to take all of these y values and then cut them in half and subtract 1. Well, half of -8 is -4, and subtract 1 is -5. And I can do that for all of the points. And now I can plot these points to get the graph of my transformed g of x function. And then I'll go ahead and connect them. And there we have the graph of g of x, which is a transformed version of f of x. Must know number 5, the inverse of a function. Let's start with the notation. The inverse of f of x is written like this, where this -1 is not an exponent. It doesn't mean to the power of -1. It's not the reciprocal of f of x. It's the inverse of f of x, where an inverse function reverses another function. For example, if f of a equals b, for an inverse function, the inverse of f at b would actually equal a. Or another way of stating that is that the inverse at f of x is equal to x. And both of these are just different ways of saying the same thing. If I take the output of f of x and I sub it as the input into the inverse function, that inverse function actually outputs to me the original input, x, on the original function. So it just undoes all of the operations that f of x does to x to return just the x value. And if we're to compare the graphs of f of x and the inverse of f of x, the inverse of f of x is just reflected across the line y equals x. And the graph of f of x and its inverse actually share all of the same points, but their x and y coordinates are reversed. And now let me demonstrate all of these properties to you with an example. The example says, if f of x equals 2 to the power of x, let's graph the inverse of f of x. So to graph the inverse of f of x, let me start by getting some key points for the graph of 2 to the power of x. I'll choose x values from -2 to 2, and now I can calculate the corresponding value of y by just doing 2 to the power of each of those x values. So those are the points for f of x. Let me graph that. So there's the graph of f of x. Notice it has a horizontal asymptote at y equals 0, and it grows exponentially. What I want to do is graph its inverse. To make a table of values for the inverse, all I have to do are reverse the x and y coordinates from the points of f of x. So all of the y values, all of the output values of the original function, become the new inputs. They become the x values. And all of the x values of the original become the y values of the inverse. And the reason why that works is because we know for an inverse function, if we take the output values of f of x and use those as the input for the inverse, so make those the x values, what the inverse outputs to us is the original x values, because it undoes the operations that f of x did to x. And now I can plot all those points on my graph, and you can see that this graph of the inverse of f of x is just a diagonal reflection of our f of x function across the diagonal line y equals x. And if we wanted to, we could come up with the equation for the inverse function by taking the original equation of f of x and then reverse the x and y in the equation, and then rearrange this new equation that has x and y reversed to isolate y. And then if you understand logarithms, you would know that we can rewrite this equation in logarithmic form as y equals log base 2 of x. So that would be the equation of the inverse of f of x. And now you can see that if we took any of these outputs of f of x, so for example, if I took 4 and used that as the input for the inverse function, log base 2 of 4 is 2. So it gives me the original input. Lesson number 6, combining functions. Let's look at this example. The example says if f of x equals negative x squared plus 3 and g of x equals negative 2x, let's graph f plus g of x, which is just another way of saying graph f of x plus g of x. So there's two ways we can do this. We can do it graphically or algebraically. Let me show you the graphical method first. Let me start by getting points for both my f of x and g of x function. I'll choose x values between negative 3 and 3, and then I'll calculate y values for both f of x and g of x. To calculate the y values for f of x, I have to use this equation, which tells me to do negative x squared plus 3. So I'll take all of these x values, sub them in for x, which means square them, multiply them by negative 1, and then add 3. That would give me the following y values. And then I could graph that function on my grid provided. And now for g of x is just a linear function, negative 2x. So I just have to take all my x values, multiply them by negative 2, and I get the y values for g of x. And now I'll graph g of x. And what I can do now is use those coordinates of f of x and g of x to get the coordinates of f of x plus g of x. Right? The output of f plus g of x is just going to be equal to the output of f of x plus the output of g of x, which means just add their y coordinates together. So when x is negative 3, f plus g of x would be equal to the y coordinate of f of x plus the y coordinate of g of x, which means it's equal to negative 6 plus 6, which is 0. Next, we have negative 1 plus 4, which is 3. And if I continue adding all the pairs of y values for f of x and g of x, I get the following. And now I can plot all the points for f of x plus g of x. Here's all the x values, and here are their corresponding y values. If I graph them, I'll see I get a quadratic relationship. And now let me show you the algebraic way we could have done this. We could have come up with the equation for f plus g just by adding the equations of f of x and g of x algebraically. So I can add negative x squared plus 3 with negative 2x. And there are no like terms to collect here, but we would typically see this in proper order of descending order of degree, so write it as negative x squared minus 2x plus 3. And that's just a quadratic equation, and there's lots of ways to graph a quadratic. We could just choose some input values and calculate the outputs, or I could convert this to factored form to find the x-intercepts and then maybe use those to find the vertex. So I could common factor out a negative 1, and then I could sum and product factor this The numbers that multiply to negative 3 and add to 2 are 3 and negative 1, which means the x-intercepts of this function would be the zeros of this equation. So negative 3 and positive 1 would make those factors be 0. So there are x-intercepts at negative 3 and 1. And I see on the graph of f plus g of x, the x-intercepts are at negative 3 and 1. And then I could find the coordinates of this vertex. The x-coordinate of the vertex would be equal to the average of these x-intercepts, which is negative 1. And then I could just input that value of negative 1 into my equation for f plus g of x to calculate its corresponding value of y. And that would be 4. So the vertex would be at negative 1, 4, which, if we look at the graph, is exactly where we have the vertex. So this could all be done algebraically with the equation we make by combining the equations of f of x and g of x. Must know number 7, composite functions. Let's start with the definition. A composite function combines two functions by using the output of one function as the input of another. And there are two notations to indicate that we have a composite function. Both notations mean that f is composed with g of x, but the one on the right is more commonly used. We read it as f of g of x, where the output of g of x is used as the input of f of x. And let me show you with two examples how composite functions work. Looking at this first example, it says if f of x is x squared plus 2x plus 3, and g of x equals x plus 4, what's an expression for f of g of x? So we have to take the output of g of x, which is x plus 4, and use that as the input for f of x. So we have to replace the x's in the f of x equation with x plus 4. So let's see how that looks. F of g of x would equal f of, well, g of x is x plus 4, so f of x plus 4, which just means, once again, we take x plus 4, which is the output of g of x, and sub that in for x into our f of x function. And then we just have to expand and simplify that quadratic expression. And collecting my like terms, I have x squared plus 10x plus 27. And this would be the equation of f of g of x. Let me shrink this and do another example to make sure you understand. In example 2, it says if f of x is 2x and g of x equals x plus 3, determine the value of g of f of 4. So that notation, remember, if I write it the other way, would look like this, g of f of 4. So to evaluate g of f of 4, let's start by figuring out what is f of 4. F of 4, well, in my f of x function, just replace the x with a 4, making it become 2 times 4. So I really want to evaluate g at 2 times 4, which is g at 8. So 8 is the output of my f of x function when x is 4. So I'll use that as the input for my g of x function. So I'll use 8 as the input in my g of x function. G at 8 is 8 plus 3, which is 11. Must know number 8, piecewise functions. Starting with the definition, a piecewise function is a function that is defined by different rules or formulas for different parts of its domain. So, for example, a piecewise function f of x, writing its equation, would look like this, where it says that f of x is equal to the function x squared for x values that are greater than or equal to 0, but it's equal to this linear function negative x minus 2 when x is less than 0. So let me show you how we would graph this. We could start by looking at the graphs of both x squared and negative x minus 2, and then figuring out which parts of those graphs we want to use based on the restrictions in the domain. So let's start by looking at x squared. I can make a quick table of values for y equals x squared, and then using this table of values, I can make a quick sketch of y equals x squared. But based on the domain restriction, I know my f of x function is only going to be equal to x squared when x is greater than or equal to 0. So I only want this part of the function, the right side of it, using those points from my table of values. And then the other function that f of x behaves like is this linear function negative x minus 2. I can make a table of values for that function, and then I could use that table of values to graph it, and it only behaves like negative x minus 2 when x is less than 0. So I can get rid of the right side of this function. So notice these points are the points that make up the left side. But we don't actually want to include this point right here when x is 0, because it only behaves like negative x minus 2 when it's less than 0. So I don't want to include the point when x is 0. When x is 0, it looks like the x squared function. So when x is 0, the function is up here. So how I indicate that when x is 0, the function is up here and not down here is I make this point an open circle instead of a closed circle. This shows it equals this negative x minus 2 function for all x values less than 0, but not at an x value of 0. When x is 0, it behaves like the x squared function. Must know number 9. Even and odd functions. Even functions are functions that have line symmetry at the y-axis. And the algebraic rule that these functions follow is that the value of f of negative x would always be equal to the value of f of x. And that's because of the line symmetry at the y-axis. Whether you move x units in the negative direction or x units in the positive direction, the function should be at the exact same height, the exact same y value on either side of the y-axis. So let's look at an example of an even function. This polynomial function is an example of an even function. If I show you its graph by first making a quick table of values for it, notice that f of 1 is equal to negative 2, and f of negative 1 is also equal to negative 2. F at 2 is equal to 7, and f at negative 2 is also equal to 7. As long as you move the same distance to the right or left of the y-axis, the function will be at the same height. And we could visualize that. If I plot these points, we can see what the graph of this function looks like. Notice there is line symmetry right at the y-axis on the graph of that function. Moving 2 to the right of the y-axis, the function is up at 7. Moving 2 to the left of the y-axis, the function is also up at 7. And we can prove that that rule of f of negative x equaling f of x holds true for all x values by coming up with an expression algebraically for f of negative x. And to do that, I just take negative x and make that the input of my f of x function. So change both of these x's to negative x. And this could be simplified using my power of a product rule. This exponent of 4 goes on both factors of the base. It goes on the negative 1 and the x. And this exponent of 2 goes on both the negative 1 and the x. And then when simplifying, negative 1 to the 4 and negative 1 to the 2, those both become positive 1, leaving me with just x to the 4 minus 2x squared minus 1, which notice this f of negative x equation is exactly equal to the f of x equation, which proves that this is an even function. Now let me shrink this and let's look at odd functions. Odd functions have point symmetry at the origin, and algebraically, the equation of f of negative x would equal the negative of f of x, meaning the outputs of f of negative x and f of x would have the same absolute value, but they would be the opposite sign. So let me give you an example of an odd function. If I were to make a quick table of values for this function, and then plot the points to see the graph, analyzing the relationships between the points, I notice that f at 1 is negative 2, but f at negative 1 is positive 2. So looking at the graph, if I move 1 to the right of the y-axis, the function is down here at negative 2. But if I move 1 to the left of the y-axis, the function is up here at positive 2. So the y values of these 2 points are the same absolute value, but they're opposite signs, which is what the rule states. F of negative x is equal to the negative of f of x. And the reason why this is called point symmetry is because at this point at the origin, if we were to use that as a rotation point and rotate this function 180 degrees around that point, it would look exactly the same. So I've made a copy of the graph, and I'm going to slowly rotate this around 180 degrees so you can see that it would still look the same. Notice even when rotated 180 degrees, the shapes of this function look exactly the same. And now let me show you algebraically how we can prove that we have an odd function. I'll have to come up with an expression for both f of negative x and the negative of f of x. We'll start with f of negative x by using negative x as the input for x in my f of x function. And then applying my power of a product rule, negative 1 cubed is negative 1. So I get negative x cubed plus 3x. And now let's look at an expression for the negative of f of x. So I just have to multiply my f of x output by negative 1. And when I distribute that negative 1 to both the x cubed and the negative 3x, I get negative x cubed plus 3x. So notice the equation of f of negative x is exactly equal to the equation of the negative of f of x, which proves that this is an odd function. Let's know number 10, asymptotes. A vertical asymptote is a line x equals a that a function approaches but never touches. And a line of the format x equals a number is a vertical line. So this function that we have the graph of on the right has two vertical asymptotes indicated by these two dotted vertical lines. Notice the function gets closer and closer and closer to those dotted lines, but it never touches those vertical asymptotes. And from an equation, the way to know that there's a vertical asymptote at the line x equals a is if you evaluate the function at a value of a and you get some non-zero number divided by 0, that's an undefined expression and indicates that there is a vertical asymptote at x equals that input of a. And when looking at a graph, you'll know there's a vertical asymptote at x equals a if the limit of the function as x approaches a, either from the right or left side of a, if the limit of that function is equal to plus or minus infinity. And we can see from the graph, as the function approaches negative 2 from the left, it goes up to infinity, but as it approaches negative 2 from the right, it goes down to negative infinity. And that's always going to be a function's behavior as it approaches a vertical asymptote. It's always either going to go up to infinity or down to negative infinity. So for this rational function whose equation is f of x equals 1 over x plus 2 times x minus 4, notice if I evaluated this function at either negative 2 or 4, I would get 1 over 0, which are both undefined expressions. And because it's a non-zero number divided by 0, I know that indicates there's a vertical asymptote at those inputs of x equals negative 2 and x equals 4. And also if I was to look at the behavior of this function as it approached either of the vertical asymptotes, let's look at the vertical asymptote at x equals negative 2. If I found the limit of this function as it approaches negative 2 from the left, it goes up to infinity. And if I found the limit of this function as it approaches negative 2 from the right, it goes down to negative infinity. And that's always what will happen. If there's a vertical asymptote at the x value you're approaching, whether you're approaching it from the left or right, the limit should be infinity or negative infinity if there's a vertical asymptote at that x value. Now let me shrink this and let's look at horizontal asymptotes. A horizontal asymptote is a line y equals b that a function approaches as x goes to plus or minus infinity. So how we could write that, we could say there's a horizontal asymptote at y equals b if the limit of f of x as x goes to infinity equals b, and or the limit of f of x as x goes to negative infinity equals b. So basically, when looking at the graph of a function, as you go forever to the right, so as x goes to infinity, or as you go forever to the left, so as x goes to negative infinity, if either sides of that function start to approach some horizontal line y equals b, then there's a horizontal asymptote at that horizontal line y equals b. So I can see in the graph of this function that we have, as we go both to the right and left, so as x approaches both infinity and negative infinity, the function seems to be approaching this horizontal line y equals 0. That's why there's a horizontal asymptote for this function at y equals 0. And I can prove it's at y equals 0 using an algebraic method that I'll show you below, and then show you how I could calculate the limit of this function as x goes to infinity. So here's the equation of that rational function, and I expanded the denominator from what we had before up here. The denominator was in factored form, but I put it in expanded form because now to find this limit as x goes to infinity, there's a trick. We actually just divide all of the terms in this rational expression by the highest power of x that's in the denominator. So I divide all the terms by x squared. Or algebraically, what's happening is we're multiplying top and bottom of this function by 1 over x squared, which means all of these terms get divided by x squared. And when we do that, we get the following equivalent limit. And now we can look at what happens to the value of all of these terms as x goes to infinity. Well, 1 over x squared, 2 over x, and 8 over x squared as x gets infinitely big, all of those fractions start to approach 0, which means that this limit would be equal to 0 over 1 minus 0 minus 0, which is just 0 over 1, which is 0. So this function, as x goes to infinity, approaches a y value of 0, which means there's a horizontal asymptote at y equals 0. If you made it all the way to the end of this video, I hope you have a great understanding now about how functions work. If you're not already subscribed to the channel, make sure you do that and leave a comment about what you want to see a top 10 of next. Jensen Math!